right if we do yours just after lunch? You ready? You're right. Okay, good stuff. Thanks. Okay, Benji. I won't interrupt, I promise.
There's been a lot of cool businessy sounding things, and as a researcher I feel it's my responsibility to actually take this back to the rock face and talk about what we're actually talking about here without all the big fancy hand waving and business words. So I'm going to do my best at that now. If there are questions, feel free to ask as we're going through. So I think a good place to start is what actually is AI. Everybody knows it's this thing that everyone's heard about in the last 2 years, or maybe a bit longer, and is changing the world and taking away everyone's jobs and magically making money fall out of the sky. Turns out it's got a slightly longer history than that. And so we can actually look back to the days of ancient Greece, where there was this guy called Hero of Alexandria, and he built some of what are known as the first automata, and these kind of automated machines. So this is an example I particularly like, where you've got water flowing out of that fountain over there, and these pipes are set up in a way that as it does, the water flows past the pipes and it sounds like the birds are chirping. In the meantime, it's busy filling up this box, and through this whole contraption at the bottom, which is weighing down this little bucket, it slowly turns this pillar, and then the owl looks at the birds. When that happens, the water is at such a level that they stop chirping, and then the owl turns back, and when it's reached a sufficient point, they start chirping again. So it's a very simple mechanical device, but this goes to show that these kind of ideas of automating things have been around for a couple thousand years even. But let's fast forward a little bit from there and look at what's now called good old-fashioned AI, which is what people would usually refer to as AI. We're looking any time from about the 50s to the early 90s and even a bit further on. And that's what I'm sure most people have come across at some point in their studies, this whole idea of formal logic, that you've got these predicates that can be true or false, and then you've got all these beautifully sound and complete logics defined over them, that you can say that if A is true and B is true, then A and B is true, and you can talk about the implications of these things. So that was very cool, and it turns out a lot of interesting representations were enabled by this. Particularly getting a bit more sophisticated, and you get predicate logic. So now you can actually start referring to terms the way that might be useful to people. So you can say X is to the left of Y, or Sarah is the mother of Bob, and you can start making inferences about these sorts of things. So you can say if someone is someone else's mother and this person has this sister, then you can infer that this is someone's aunt. Alright, so you can start making some interesting inferences about the world using this kind of logic. And then you could go even further with this. So there was a lot of really nice work talking about planning using these sorts of logics. And this has been used for all sorts of things. So you say, I've got some initial configuration, I've got some goal configuration, and some understanding of the physics of the world. So I can describe these using these kinds of predicates, and find plans that structure things in such a way that I get to the end configuration. And this was also incredibly successful. So these kinds of logics and these kinds of planning systems have been used for a number of logistics problems, famously for doing things like managing docks and unloading ships, but also spacecraft have been flown on this kind of logic. So we got very far with that. But there was one minor problem with all of this, and that's that the world tends to not be so well structured and complete in the way that we can reason about it mathematically. Now, this is a little bit tricky because, I want to describe a giraffe, and I can come up with a whole lot of terms that I can use and reason about, but the real world doesn't always behave in that way. So take like an actual example of some handwritten digits. Now, in this case, I could ask you to come up with some rules to describe these things, but the odds of you coming up with a succinct set to describe a particular character, maybe a 7, is pretty small, right? And it's going to be a lot of work. You're going to have to think of all the different bits and pieces that could go into a 7. Sometimes there's a line across it, sometimes it's curvy, sometimes there's a sharp point. And this started becoming a problem, because this is quite difficult. And this is where we see the introduction of what's now called machine learning. So the idea is that many programs are hard to write. For example, a face detector. Right? If you were to come up with a set of formal rules to describe a face, you might say, well, there are these 2 things called eyes. Actually describing that's a whole other problem, and a nose, and a mouth, and blah, 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 blah. And then your system's going to have an issue when you come across a person with 1 eye. Right? So this is a difficult challenge. But people realized that although these programs are hard to write, to come up with these rules, you can give them examples of what the input and output should be. I can give you a picture and say this is a face. I can give you another picture and say this isn't a face. And so if you know what something looks like and what it is, the whole idea here is that the machine should be able to figure out the rules for itself. And that's really fundamentally what the big change has been. So then just to tip my hats to the businessy folks, which, sorry if I've offended anyone, I'm just going to just briefly run over some of the basic terminology that people tend to throw around here without really knowing what they're talking about. So first we've got AI, artificial intelligence, and this is a nice, well, there's a couple different definitions, but generally it's referred to as the nice big broad umbrella field wherein all this stuff lies. And what is this stuff? These are all these techniques and software and algorithms that are capable of some sort of intelligent behavior. I'm being a little bit hand-wavy there, but that's generally what people refer to. Then, at the core of artificial intelligence, or at least modern artificial intelligence, is this idea of machine learning. And that really is about the algorithms that we want to be able to make predictions and to find something important in our data. And that's what everyone's making all these zillions and billions and trillions of, is being able to collect some data from somewhere and do something intelligent with that to make some predictions or understand something about it. Right, and then you can go on to one of the current big hot topics, is data science. And this really talks to a whole pipeline, of which machine learning is one step. So this is the whole process of going from talking to your clients and understanding the data, or even collecting the data, curating the data, keeping the storage set up and operating in the right kind of way, doing the machine learning, which is really about extracting the insights, and then delivering on those insights and doing something with it. So it's really this whole pipeline, and talks to having quite a broad range of skills to make the whole thing work. And finally, there's there's data, big data, which is this idea of, there's something business loves at the moment. And this is the idea of you've got these huge data sets, and what do you do with that? It turns out there's a lot of interesting problems there, because typically this comes in at a really fast rate, and you're dealing with possibly unstructured data in the form of tweets, and you could have images and all sorts of things. And typically in your kind of large international examples of this, your data comes in at such a rate you can't do anything particularly sophisticated with it, because given the rate and the volume and the amount of it, you typically don't have the ability to store everything, so you need to pull something out of it pretty quickly and then get on with whatever you're trying to predict. So we kind of have this flow where we start with artificial intelligence as a broad umbrella area, machine learning as the core technology that enables a lot of what people care about now. Data science is a pipeline, typically for businesses, that incorporates machine learning, and big data refers to these specific issues where you've just got huge quantities of data and you can't rely on the traditional ways we analyze these things. And in my head, I think of it as people use these words, they're more of a scientist, and those words are more of a business people. Anyway, so AI itself is very multidisciplinary, and it draws its roots traditionally from computer science, but from a whole lot of different fields. We take a lot of inspiration these days from psychology, from neuroscience, but obviously there's heavy foundations in maths and statistics, in various kinds of engineering, and so on. And what it actually is, as I said, being an umbrella term, has all these other things that go on inside it. So learning is just one component. There's aspects of perception and planning and representing knowledge and so on. And there's a number of applications that are enabled by this, and I'll talk about all of these aspects as we go through this talk for the rest of the day. But this can range from everywhere from understanding language to proving theorems to personalizing healthcare or adverts delivery to even playing games. But first, I think it's useful if we look at a little bit of an example. So imagine we have this problem where we wanted to classify handwritten digits. This is like the very old hello world problem of machine learning. So we might have some digits written on an envelope somewhere, and we'd like to post them out, so we need them digitized. So what we really want to do is to learn some function that gives you the label, which is a function of the image. So if I give you this little picture of an 8, I want it to spit out, this is the digit 8. And the problem is that we've got this data and we want to map it to a numerical class. So how do we do this? We think of this function f as some model of the digits. And we're going to go through some sort of training parameter, which tweaks the training process, which tweaks the parameters of the model. So inside this model, inside this magical function f, are some parameters, and the whole point of doing the learning, that is machine learning, is to figure out what the right value of those parameters are. So in some sense, it's just an optimization problem, given a set of data. So we're going to present this algorithm on this model with a whole set of these images where we know what the true labels are. And then at test time, we're going to get some new images we've never seen before, and we want to be able to predict the label. Now this is really at the core what the machine learning problem is all about. So let's go through what this might look like. So let's just say, for a very small toy example, you've got this problem where we're given two features: the size of an animal and how domesticated it is. And we want to predict if it's a cat or a dog. Right? So we've got input and output. And the idea is we're going to see a whole lot of these things at training time. So someone's going to sit there and painstakingly give us this detail, say, oh, here's some information, and this was a dog. Here's another one, this was a cat. But then we're going to go out into the real world and deploy this and get new examples we've never seen before. And the whole point of machine learning is we want to generalize from the examples we've seen before. So you might have something like this. You might have your two axes, domestication and size, and two data points, those little spots. Now the idea is our model, in this case, is a straight line that's going to fit somewhere between these data points. Because I'm going to go out into the real world and give you a new point you've never seen before and ask you what that's likely to be. But obviously that's pretty terrible. So if I've only got two data points, I can fit infinitely many straight lines between them and separate the two. So that's kind of useless. So I can get some more data, and then I'll get a better fit of the parameters of my model. Now, going back to whenever one learns these things at school, the parameters of this model are going to be your slope and your intercept. You know, y equals mx plus c, all that kind of stuff. And so we're trying to fit the m and the c in that case. And the more data we get, the better we can fit this line. And the idea is, once we have a trained model, you then want to go out into the real world and query it with a new point. And you can already start getting an idea from this very simple example of why having lots of data is important, and why machine learning and AI couldn't explode until we had large storage capacities, until we had sensors everywhere in the real world. Because even just this one straight line needs a whole lot of data to get a very good model of what we're trying to do. So the current way of looking at models, which these days everybody knows about, which is deep learning, is very loosely inspired by the most successful computational device we know, which is the brain. And that's built up out of billions and billions of neurons. And so we've got some very loose inspiration here. And we get this quite elegant little model, which is our artificial neuron. And this is one of the core elements that, at least deep learning, there's a number of different ways that machine learning actually works and a number of big branches of it. But that's clearly the popular one at the moment. And this is based on this idea that you've got input neurons that come into an output neuron. So in this sense, you've got a neuron in the brain, and it connects to a whole lot of other neurons, and they pass electrical signals around. And they're little tiny computing devices that, when they receive a set of inputs, they can do some processing and fire of their own accord. And that's kind of what we do here. So we have some inputs, and they come along with some connections into the output neuron. It does a little bit of computation and fires. Now the three elements of this is you've got input neurons, you've got the output neuron, and you've got the connections between them. And what this really does is this kind of models this idea that you might have some properties that you care about. So this could be the level of domestication or the size or something from our previous example. We might be trying to predict the label, and we've got these connections which give you some sort of importance. They could be positive or negative. They're essentially just scalar numbers, and they tell you how much we care about each property. And these are the parameters we're trying to learn in the model, and that's what we need the data for. And the way this basically works is we're going to give it a training example. So we've got this example that sets up these properties. We propagate it through, and it makes a prediction. And it says this is a dog. And we're like, yay, that's exactly what we wanted. Right, then we give it another example. We give it this one, we fill in the properties, we pass it through, and it says, that's also a dog. Right, so clearly this is an error. And the whole process of learning is really about error correction. So we tell the thing, no, you've made a mistake, that's a bad algorithm. This was actually a cat. So now there's an error here. And we do the standard methods called back propagation. And essentially that means we propagate back the errors. So we say, whoever was most responsible for messing that up, we're going to change the connections so that you give the right prediction next time. And you repeat this over and over again with all your different examples until these sets of weights converge to something that's giving you the right answer consistently. And that at the core is a very basic idea of how learning is working. And again, you can see why it's important to have a lot of different instances and examples to train from to be able to build a good model. Now, in this case, that worked really well when we were using these features of size and domestication. But if instead the two features I had were number of ears and number of eyes, it doesn't matter how sophisticated my model is, there's absolutely no way I could tell the difference between a dog and a cat. Right? No matter how hard I try. So this is a problem. And this traditionally was one of the big problems in machine learning. This is called feature engineering. Right? How do I figure out what the right features are to tell the difference between cats and dogs that actually lets me perform this task successfully? Right? So at some silly level of abstraction, if I had a feature that says it's a dog or a cat, or maybe it barks or meows, right? Just that one feature, you can use the stupidest algorithm you can think of. It should be able to classify them. So there really is this notion of your predictions are only as good as the features that you have, and actually the data you have as well. Now this was, as I said, always a huge problem. So the whole insight behind deep learning is we can actually learn these features. And the idea is we stick other layers inside our network where we give as the input the most basic elementary things we can and as much information as possible, and we let it learn the higher level features. So that's where things like domestication and size should come up, right? Because each of these, you can think of all these blue nodes connecting to one green one. It was the same network we had before, but now we're replicating this. And the idea is that those hidden nodes eventually learn to be the features that we care about. Now obviously in this case there's a whole lot more parameters, which means we need a whole lot more data to actually learn anything useful in this case. But fundamentally that's what deep learning is all about, is that we can now learn the features that we had to spend ages working on before. We had to get domain experts in. So now we can just, as machine learning experts, we don't need domain experts anymore. We can just do this all ourselves, which is pretty great. So to give a kind of intuition of what gets learned here, look at a simple instance of what happens when you're trying to learn to recognize faces. Now, I'm not going to go that much into the techniques that are going on here, but the idea would be your input image would be a face. And at the first level, you tend to learn features. Again, I'm not going to describe all the technical details, but you learn these features. And what these amount to is basically edge detectors. So you learn that if I want to be able to discriminate between faces, the most basic thing I need is to figure out what edges are, tell the difference between light and dark adjacent pixels. Once I've got something to do that, because the raw input here is just a set of pixels, then I want to be able to construct from those features something more useful and intuitive. So you can piece together these little edges and learn concepts such as eyes, noses, and mouths. And again, then you can piece those together and get the notion of a face. So this is really what we're doing. Through repeated layers of the same thing, we're learning different levels of abstraction that allow you to make the decisions you need to make at different levels. And what's also very cool is that this mimics exactly how the brain works. Typically, there's 6 layers of neurons deep throughout the brain. And so again, the methods that we've had to develop to solve these problems turns out are mimicking biology, which is really satisfying, because this is how the brain solves the same problem. Now you can do lots of cool things with this. So this was one of the results from one of the breakthrough papers where they trained on a huge data set, the ImageNet data set, and they had to predict on images it hadn't seen before, it had to predict the top 5 descriptions of the images. So you can see here, for example, that second one, its number 1 prediction was container ship. The red one is the correct one, so it got that right. On the other hand, other ones that it might have messed up, so this one that it got wrong, it predicted Dalmatian instead of cherry, right? Which I think is a pretty legitimate mistake to make. Now, this is already a few years old. This is from 2012, but this is what really put deep learning on the map. No one took it seriously before this paper came out, and already this is incredibly impressive. But things have come on a long way since then. So, you know, we've now got a similar extension that came out 2 years later, was even able to distinguish between different types of cats and dogs. Right? Very similar kind of technology. And that's part of the power of this, is that fundamentally we're using the same building blocks to build all of these algorithms and methods. And again, that's very cool because we're reusing all our knowledge. And we're saying, okay, we're going to tweak this slightly, but all that's fundamentally different is I'm giving it different training data. Right? So this isn't requiring any in-depth analysis of what makes a dog or a cat different. I'm just throwing it at the same algorithm and saying, here, I can label these things for you, figure out what to do from here. And then there have been a lot of fun things that have come since then, drawing on the same ideas. So you can do style transfer, you can take a photo, give it a painting in the style of an artist, and ask it to reproduce it in that style if you want, which is kind of cool. And it relies on all these properties that we're learning, the fundamental components of the image. So if we tell it to bias them to look like something else, we can do funky things like this. But actually, fundamentally, in a lot of, say, business applications, for example, what we care about is data that changes over time. And that's not what we were looking at there. We're looking at a very static case, a dog versus a cat, recognize different kinds of images and so on. So here we look at something a little bit different. These are called recurrent neural networks. You've got a similar structure to before, with some input, something magical happening in the middle, and some output. So you can think of it as that model I had before on its side. But what we're trying to do is predict the next thing. So if I have an H, the next thing I might want to predict is an E, and that would happen in a sequence. So, and essentially what's happening here that's different to the previous case is we're tracking some sort of memory along the way. So we've got this kind of memory component that's saying, my next prediction, right, because the first time I see an L, my prediction should be an L for hello, but the second time I see an L, I should predict an O. What's the difference there? I've got some sort of context. So the whole idea is we're moving now from these models that can just say, I see some features and I can make a prediction, to I see some features and something happened in the recent past that gives me context that allows me to make different predictions. So again, just to walk through a little example that's quite cool. So this is a system that was trained on Leo Tolstoy's War and Peace. Why? Because it's a ridiculously big book. And so there's a lot of training data in there. And all that this was trained was to predict the next character. So we're looking at a model here that all it knew about was characters. We're not even telling it about words. For many decades, this is how your translation models work. They used n-gram models, which means we look at sets of n consecutive words. The problem is the bigger n is, the more data you need. And so often you'd say, given 2 words, can I predict the 3rd word? And this is how all your translation type stuff works. But now we're not even saying words exist. We're just feeding it the raw characters. And the cool thing here is if you make it read the book 100 times and get it to generate text, it's pretty poetic. Okay, but basically it does have some notion that words exist. So there's groups of letters with spaces, but that's pretty rubbish. If I make it read it a couple of 100 times more, then we start getting a bit of structure that looks like something we'd see in English. So you've got open quotes and closed quotes, although it's not always right. You've got this idea of full stops followed by capital letters. You've got that words are getting to shorter lengths. A couple hundred more times reading the book and you start getting a few common words popping up, which is really cool. And we can keep going with this. We can start getting something. Eventually, after you've let this thing read the book 2,000 times and learn from that, you get something that is pretty Englishy, right? There's no context between words over long-term dependencies, but this was a very simple model that I showed. But what's really neat about this is for many decades you've had computational linguists arguing about if language is innate or learned. Turns out you can learn language. You You just have to read this book 2,000 times. So that's cool, and then people have done all sorts of interesting things, like generate poetry by reading a whole lot of other poems. So this is completely computer generated. And there's plenty of examples, and some of these are actually pretty reasonable. And now, I'm sure everyone's seen these demonstrations of these algorithms writing scripts and for movies and all sorts of things. So that's pretty cool. And again, it turns out if you just have enough experience of some domain you care about, you can be pretty good at it. I mean, there's also a lot of rubbish that's produced, but that's why these are ongoing research areas. What is very exciting though is you can combine ideas from these kind of temporal or these time series models that deal with data like text with the kinds of models I mentioned earlier that deal with images and combine them. So this was a very exciting piece of work where what you could do is plug the two components in together. So you could, for example, give it this image it had never seen before, train it at the character level on these kinds of images, and ask it to produce a caption. Right? So given this image, it says a group of people shopping at an outdoor market. There are many vegetables at the fruit stand. Obviously, that last little bit's a bit new, but that's not bad for an image it's never seen before if it had no prior experience of language other than just seeing thousands of images with captions. All right? So that's pretty powerful, and that actually gets this idea that somewhere in these hidden layers is some sort of representation that you might generously call understanding, right? You could argue that this algorithm has some understanding of what's going on in this image. And there's many examples of this now. So this is an extension of the same kind of model, where not only was it doing that, but it had an attention model. So given an image, it had like an eye that it would look at different places around the image. So you can see, for example, the word in bold. What it was looking at was the bit highlighted in white. So for this image it had never seen before, a woman is throwing a frisbee in a park. And when it decided to generate the word frisbee, that's what it was looking at. All right, so again, I think this gives a nice understanding that if you have a strong enough concept of what the correlations are in data, you can actually get to something which is a reasonable interpretation of what's going on in the world. Right? A group of people sitting on a boat in the water. Like, that's some fairly profound contextual understanding of the situation. All right, so moving on from here, what can you actually do with this? And there's obviously innumerable applications for these kinds of technologies. So the most obvious one is I want to be able to make predictions and to classify things. Right? So this might be predicting some sort of financial information. I've got data points at various time sequences, and I want to predict something going into the future. Right? That's a nice, straightforward thing. You can predict crop yields, you can predict weather, whatever you want to do. And alternatively, you might have some classification problems. You want to classify someone as a risk of fraud or not, for example. And so these are really your cornerstone problems that pop up in this domain. Something else that's become very popular, particularly with Amazon and Netflix, is the whole idea of recommender systems. That gives you some notion of customer understanding, right? You've got your customer that's doing something online, and you want to be able to make predictions of what other things this customer should buy. And this is really based on this idea that if you see a customer who's bought certain things and another one who's bought similar things, and this one likes the new product, the Coke or whatever, you can recommend that to the similar people. And this is this idea of saying that people are similar based on their behavior, which is really the right way to discriminate between people. You can do other interesting things, like understand documents and speech and images. There's a lot of work at the moment on sentiment analysis. Are these tweets angry or happy? We had, whereas in the UK, there were a set of academics there that put together this cool machine. It was like a giant cupboard that made music, but it would search its Twitter feed for comments and reviews on it, and if they were good ones, it would compose happy music, and if they were bad, it would make sad music. So you can do all sorts of interesting things with this. And even now, moving forward, you can recognize emotions on people's faces in their tone of voice. There's several apps out now that can listen to someone speaking and tell you what mood they're in from their voice samples. So there's a lot of exciting work around this as well. You can also generate stuff. So this is a bit out of date now. A friend of mine at MIT did this. Trained on tweets of Trump and then generate some more, and they seem pretty legit. This was back during his election campaign. But But you can now do much more interesting things. So there's a lot of work now on generating videos and speech that sounds like and looks like someone's saying things that they never actually said, which has a whole lot of societal implications in itself. Do you ever trust anything you see on video ever again? Right, obviously a big thing for business is for anomaly and fraud detection. This is given some patterns, you want to get an idea of what regularity looks like in your domain. And this could be fairly complicated because people might do different things under different situations. So it might not be as simple as saying there's a trend in this data, but you might need to understand something about the latent structure. Right? I might do things differently when I'm not in a relationship and on holiday and my parents are in town. Right? And this is not information that you have, but if you see enough people and the kinds of trends that you expect people to have in the long run, these are the kinds of insights you can pull out of your data. And then something else that's very exciting is speech recognition and translation. This was mentioned a bit earlier, but now a lot of this stuff is actually happening on the fly. There's various speech translation systems that you can almost talk and will fluently translate. I don't know if you all saw from about October last year, Google Translate became pretty amazing as they put deep learning systems into play. And there's a lot of really exciting stuff. I've got some colleagues at Google and Facebook that are always trying to one-up each other on their translation systems, and they keep boasting, we've got the best one in the world. Yes, but only for the next month. And that's also quite exciting. And to have these kinds of apps that you can walk around a foreign city and get instant translations of anything really opens up possibilities for better communication. But then all of this raises an interesting question. Like, fundamentally, why do we want to make these predictions? So I've shown a whole lot of different systems for classifying things, for understanding things, for predicting things. But fundamentally, what's the point? Let me tell you a quick little story, which is quite typical of many different pieces of consulting work. You might have an online store, and they find they've got a problem with churn. So they've got a whole lot of customers that run off. Now, it's a lot of effort to go and keep finding new customers to replace these customers and keep your business going. Ideally, you don't have people leaving. But it turns out that this happens a lot of the time. So the board gets together, and they decide this is a huge problem, and they bring in some analytics company to have a look and figure out what's going on here. Now, they will go through and they'll do all the standard things of trying to understand the different sectors of the customers, blah, 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 all that boring stuff, and give you some insights into what's actually going on with your customer base. And they take this back to the board, and the board's very excited that, cool, we can actually predict now that 73% of our customers are going to disappear, particularly in these certain situations. What we're going to do is give them coupons, and nothing changes. And then they go back to this analytics company and say, you didn't help us. They said, of course we did. We could predict exactly what was happening with your customers. And they said, no, but nothing's changed. They're still all leaving. And the problem here was not with that bit, it was with that bit. So we've got what you might call this decision cycle, where you get some sort of observation of what's happening with the phenomena you care about, and then you're going to make some predictions about what's going to happen, and then you're going to intervene to try and change what's happening. For those in the know, this is kind of like a control theory problem. But typically what happens is that bit is what has been automated for the last number of years, and this bit is done by people. Right? So it kind of looks like that. Right? So you've got your data, you've got some nice fancy algorithms that can predict things. You give this to the HR department or the sales department or the board or whatever it is, and they give some intervention and you carry on observing. Now the fundamental problem here is that one part of this is optimal and the other is terrible. Right? And this is often why data science and AI contracts fall through, and there's all sorts of problems with this pipeline. And honestly, it's because there's humans in the loop. So this is actually what fundamentally is the robotics problem. So here's a setup one of my students is working on. Now, in robotics, you've got this idea where you want to see something about the world, but you can't see the whole world. It's partially observable, but you can do things. Now, this is cool for a number of reasons. Firstly, doing something can get you more information. I can move things out of the way to see what's behind something. I can move around something to see what's at the back of it. But also it means I can think not just in the immediate future, which is what happens with supervised learning, where I'm just trying to predict one thing, but I can think out the effects of a whole sequence of actions. Right? So I can actually plan optimally to maximize some utility that I care about. Right? So you might have a situation where you have to perform a whole sequence of actions, and each one's contingent on what happened before, as well as the situation of the world you found yourself in. So you've got to make these decisions looking into the future. And it turns out this is actually where the cutting edge of artificial intelligence is at the moment. So in this whole idea of making decisions, what you typically have is some agent that's operating in an environment. We call a decision maker an agent in general, but this could be a robot, it could be a human, it could be a software agent. Right? And typically what happens is at each time step, your agent's going to take an action, the environment's going to change as a result, and you get some sort of goodness measure, something good or bad will happen. And often the problem is that the good thing or the bad thing only happens somewhere down the line. Right? You don't know immediately that the step you take is going to end up with you winning the lottery or getting hit by a bus. It's like the first on a long sequence of actions. And you really want to make your decisions based on what the long-term effects are. So what really has to happen here for an AI system is it has to learn how its actions affect the environment. It's got to learn what is desirable in the environment. It's got to use all of that to compute the best thing to do in any situation. Right? So clearly that's a difficult problem. So prediction is just one little piece of that. But now we need to move to the full state of actually making decisions. And kind of, in a caricatured sense, what you really want to know is if I'm moving around some environment, at each point, what is the best thing to do there? Not because of what's going to happen in the next thing. Something good might only happen when I get to the reward in the end. But I need to make the right decisions here, which might be 20 steps behind, or 20 years behind in the long run, so that I get to the desirable outcome. And this is something humans are terribly bad at. Right? Very few humans can actually make optimal decisions now to affect what they want to happen by the end of the week, or the end of the month, or the end of the year. And this is where we're seeing some real power coming in. Now, it turns out it's hard to do testing and science in 20-year decision-making horizons, so we turn being geeks to things like computer games, because these have these nice properties where you want to take a whole sequence of actions and eventually something good's going to happen. You might accumulate some score along the way, but really you want to win the game. And to do that, you have to get into the right position by taking a whole lot of actions along the way. And there's been a lot of work recently in the last couple of years, particularly from DeepMind, in looking at this kind of problem. And we're now at a stage where with one single algorithm, they could play it in 50 different games, these old Atari games, which was that cool. And kind of all the ones above that line are played better than humans just by using quite a straightforward algorithm in this case. There's still a number that are difficult and are still being worked on. But the cool thing was nothing needed to change. All you did is you gave your system the screen, so it could see the different pixels. You told it there were certain actions it could take, and it had to figure out everything else. And using these kinds of technologies I've been talking about, these are the decision-making paradigms you want to be able to bring in. So just as an example, if I can, where's my mouse? Go back. Okay, anyway, I'll talk around this. So this is going to play Breakout, which is a game that anybody who was around in the 80s would remember. And again, what this is given is just the pixels, and it has to just take some action. So this is just quite a nice intuitive example. So when you start out after just 10 minutes of training, because at the beginning it would be completely hopeless, right? So at this point it doesn't even know what the left or right arrow do. And it's learned this from its own experience. So you can see it keeps losing most of the time. It's controlling this paddle, for those who don't know, and you've got to try and bounce it into these colored blocks to delete all of them. So after about 10 minutes of training, this is how amazingly good it is. So it knows nothing about the game. You leave it training for about 2 hours. Now remember, what it's trying to do here is understand the dynamics of the game. It's going to be able to make predictions of where things will go when you interact with them. It's also going to make the right decisions to enact what you want in the long term. Now, this is essentially expert level play after about 2 hours of training. This is effectively like this thing was born, and 2 hours later, it could play this at the level of an expert. But what was really cool is a couple of hours later, it was even better. It had figured out some hacks in the game. And this we're seeing in all sorts of interesting domains. So you can see here, it's figured out that if it can tunnel up one side, which we should see pretty soon. Right now, it obviously doesn't have control over everywhere the ball goes. then it can win the game like that. Right? So that's what we mean when we're talking about long-term optimal decision making. Just for fun, I've included an example here that one of my students are working on, just playing Mario. So again, this was actually a bit of a simpler algorithm, but we'll zoom in a sec. Now it's got to avoid several different ways of being killed. It's got to make all these decisions to collect coins and be able to get to the end of the level. So this is the kind of performance that you're looking at. Remember, we're using these as proxies for real-world domains because you have to make decisions constantly. There's a rich visual environment that you have to understand something about the structure of it while you're doing that, so that you can be able to make optimal decisions that have long-term effects that you care about. Now, the most obvious example that's been in the press a lot in the last couple of years is Go, which is this ancient Chinese board game that has more possible configurations than atoms in the universe, famously difficult. The world champion was pretty convincingly defeated last year, and then in the last couple of weeks, they've released a new one that could beat that previous one 100-0, and that had no training from humans. Because part of the whole philosophy behind deep learning is when you add humans to things, it makes it worse. So just let the machines do their stuff and we'll be better off. So that was a notoriously difficult game, and that's now done. So that's not interesting anymore. So where we're now going with all our research is to other interesting domains. So we're looking at these sorts of domains that, again, mimic the real world in more complicated ways. So you've fundamentally got the same kind of structure we would recognize in our daily interactions with the world. And again, it's about trying to understand the structure of this, that there are walls, that what does it mean to have free space? What does it mean to have somewhere you can walk around? How should you plan? How should you map out the environment? And these are the kinds of domains we're using for this sort of problem. Another one that's, the challenge was opened a few weeks ago, is StarCraft 2. I don't know if any of you are familiar with this, but basically this is a very popular computer game where you have to build armies and build bases and manage resources and train soldiers and so on. And the idea is to be able to handle this scale of game. You can see that there's a whole lot going on here visually, so there's a lot that needs to be understood. There's a lot of structure, there's a lot of finesse, and there's a lot of strategy. So this is one of the kind of grand challenges that's open at the moment in this paradigm. So just to kind of pick up on some of these ideas, this is the kind of work we do in my lab. So we focus on issues around learning from your own experience and to be able to learn from the behavior of experts. I want to watch someone else do something, figure out what they were trying to do, and then how to do it better. I want to be able to learn and use individual behaviors. So again, as I'm exploring around a domain, I want to discover that, there's this thing which is opening a door. Turns out that's really useful. This is something I should get good at and be able to use whenever I need it. One thing we're very interested in our work is this idea of multitask operation. There was this notion earlier of narrow versus broad AI. You'll find most AI systems are very narrow. That Go playing agent, if you give it a board that's slightly different size, it wouldn't know what to do. If you give it a chess game, it wouldn't know what to do. So we're looking at this idea of how do I learn to do multiple different things without forgetting what I've learned already. And a lot of this amounts to trying to give our agents common sense knowledge, which should be acquired from a number of different ways, particularly repeated experience with different contexts and different situations in the environment, and also seeing what humans and other agents do. And fundamentally, all of this amounts to being able to transfer knowledge between different situations. If I learn to do something over here, if I learn to walk in this room, that I should be able to walk in other rooms as well. And when the terrain changes and gets more complicated, I should be able to learn faster, knowing that I could walk over here beforehand. So basically, all of this gives us all sorts of cool things, and we're just starting to see the beginning of this. So the most famous being things like autonomous driving, where it's very clear how that mapping works. You've got to make a whole lot of decisions that get you from point A to point B. You've got to understand what's happening in your local context, and it's very important where you've come from and what actions you take in each situation. Another big one is medical treatment. So in this case, you might have that your patient comes into your clinic at multiple times, and you want to give optimal treatment strategies over a multi-year period. So we're looking at using similar kinds of techniques now to be able to make these decisions optimally and cumulatively over time to get the ultimate effect. And maybe the feedback we get in the middle is not the most informative. But we need to be able to learn based on all sorts of ideas I've discussed here, from ideas from recommendation systems to these reinforcement learning models, to piece all these things together to be able to make these decisions. In a business sense, what you're looking at is being able to optimize your whole production, your logistics, and everything that's going on there. But more than that, you want to take a long-term view of things, and that's where things are getting exciting now. So it's not just at month one and on a monthly basis, but you want to look into the future, and you want to say, in 10 years' time, this is where I want the company to be. Okay, algorithm, get me there, right? So these are the kinds of decisions we want to make. And again, you want to close the loop so that all your predictions are done autonomously, but your actions are taken autonomously too. And that's how you get things done optimally. And you can see the exact same sorts of things happening in other domains, such as agriculture, where there's a lot of interest in this sort of work. So again, you want the whole process from figuring out what crops to plant and when to fertilize and that sort of thing. But again, you want to take a multi-year view of this, which includes when do I leave certain fields fallow, when do I plant different crops in different seasons, and so on. So all of this comes down to that decision-making problem and looking at it over a long time scale horizon. And basically that's what I mean. In short, this is where we're going with things. The observe to predict is what's hot and in the press at the moment, but we really want to take the prediction through interventions, and that's where all the research is really focusing at the moment, to try and get really optimal, sound decisions that can have the right long-term effects that you're looking for in whatever context you're working on. Thanks. And that was
okay, any questions? I think that was awesome. I know people are hungry, so we're going to have lunch right now after this. Yes.
What's always quite interesting in these things is how do you work out that fitness function. So, obviously there's games, it's simple ones, it kind of learns in itself, it's quite easy to code it. But as you move into some of these other domains, it becomes increasingly difficult to do. Are you suggesting that one danger is that you let the AI learn it itself?
Right, so this is that famous problem of having misalignment in objectives, where you don't want your AI to go and turn everybody into paper clips because it was told to maximize the number of paper clips. And that's one of the big research areas at the moment. So a lot of the work at the moment does rely on, so in the robotics domain, for example, we don't want to go directly and have these algorithms that have no prior knowledge of anything. And they start off going, ooh, what does this button do? And just flailing around randomly and breaking your multi-million rand robot in the lab it's in and everything, right? So that's like slightly suboptimal. And what we rely on at the moment is having good simulators that you can kind of work in and understand the problem and get to a certain proficiency at which you can deploy it. Now this has spawned a whole lot of different research areas, and particularly transfer learning is one that I spoke about. But there's also this notion of curriculum learning. And there what you might want to do is give your system a curriculum, as in you're sending it to school, right? And you first teach it addition and then multiplication and build up all the way to calculus. So you let it solve very simple problems in very toy domains, and each time bootstrap off what it's done before to solve more and more interesting, more realistic problems. And that's one of the exciting ways that people are looking at dealing with this problem at the moment. And then you can kind of monitor its progress, and if it's, because typically it's going to learn what you tell it to learn. And all of our worries and fears are that we might tell it the wrong thing to learn. And this way you can kind of keep an eye on it as it's learning and correct things as it's going along.
But of course what's interesting about that is we probably all don't agree on what's good and what's bad either. So
exactly. And this is where, things like the trolley problems existed in philosophy for forever. And now we have autonomous cars. The joke is, all right, we gave you guys 2,000 years, what's the answer to this question? And they look at you and say, well, it depends what school of thought you're from.
Any more questions?
Yeah.
Yep.
okay.
I've got a bunch of questions. So we can maybe.
Thank you. I always have problems in terms of using artificial neural networks. When you are classifying, maybe you're classifying objects or classifying maybe a client of the bank. Which approach is better? Artificial neural networks or maybe extension?
So it really depends on the situation, and you can't give a general answer to that. The power of neural networks and deep learning is really in the feature learning, and So you often see people are tempted to just throw deep nets at everything, just to say I threw deep nets at everything, and look at me, I'm so cool. But fundamentally, they're not always the right tool for the problem. If you already have a good set of features, then often something like simple like a decision tree or a support vector machine is the right tool to use in that situation. And actually, often it comes down to this vague rule of thumb for a problem like that, which is, as a human, if I had these features, does it seem plausible that I could figure this out? And if not, because it requires, so in the case of an image or a sound signal, for example, right, there's a lot of complex processing that has to happen. And you're not going to manage that just eyeballing it. It's clear that you need higher order structure in the data. But in many cases, that's not true. So it's really problem specific.
Okay, just quick, we can go into a lot more technical stuff as well, because I did my PhD in AI and recurrent neural nets and stuff like that. But I want to, in terms of Francis Collins, the future of deep learning, did you read that blog, Kira's blog? Yeah, no, the interesting thing there for that is, I'm just thinking of your lab, what you're thinking about in terms of your problems you solved. They're talking about geometric routines, combining that with algorithmic routines, having meta layers, and you have a library of all these different routines, and getting to more explainable type of solutions, and kind of building these hybrid solutions. And they obviously get to limits with deep learning as a geometric routine, which is just doing transformations and stuff like that. You need breakthroughs on different levels. Are you in your lab looking at those type of things as well, more hybrid type of stuff, meta layer type of stuff?
Yeah, so I think that there's two different hats you can wear when you're doing AI as a practitioner. One, you tend to have people that are more interested in the cognitive neuroscience and computational ideas from there. And those tend to be people that say, I wonder if we can figure out how the brain works and how intelligence works by building our own replications of that and studying them. And that's where a lot of the deep learning work came from. And then there's more the engineering hat, which says, I have a problem, I need to solve it. We try to be more pragmatic in my lab. I don't like the idea of being too tied to a tool. You've got to use the right tool for the job. And so, for understanding images, conv nets are the best things to use. But sometimes when there's more structure in a problem, you'd rather use like a Bayesian graphical model or something. So we try and use the right tools for the problems we're working on.
That's exactly my approach as well. Last, a bit more generic as well. You talk about the future of jobs and stuff. You've got some good examples of intervention, bringing that in. Where do you see the human fitting with that, if you from a decision-making perspective? Where's it going?
That's a tough one, and this is being recorded. So a bit closer again, so we can. There was a discussion that I heard recently that said there's humans have two ways that they can add value to things, and the one is physically and the other is cognitively. And when you had your earlier industrial revolutions, those all targeted the physical capabilities of humans, and they could retool to be cognitive. The challenge now is that we're targeting the cognitive capabilities of humans, and it's not clear that we have other things we can do. So while I think, just to be blunt, while I think in the short term there's a lot of value to be placed in augmenting machines with humans, I think in the long run humans will just add noise to the system, and there won't be any reason to have people in things. So I think ultimately we're going to need to find new ways to construct our societies, to be perfectly honest, that rely on what you do when you have maximum production and productivity, but humans should not be any part of that. And I honestly feel that's where we're headed.
Okay, very interesting. Okay, great stuff. Any other questions? Okay, so we're going to have lunch now. So, and then right after that we've got the IBM discussion. Okay, cheers. Thanks.
Yeah.